In this video, we are going to be going over the reactions from first semester organic chemistry and some of the mechanisms that were studied. Let's get started by talking about substitution and elimination reactions. When we're talking about these kinds of reactions, we are going to be using as a reactant alkyl halides. Remember that alkyl halides, as you can see in the examples below, are going to be alkanes that at a position within that main chain is bonded to a halogen, which is here demonstrated by the letter X. Just to be reminding you guys of where those halogens live, they live in group 7A of the periodic table. And the halogens include fluorine, chlorine, bromine, or iodine. Now, these alkyl halides can undergo substitution reactions or eliminations depending on the nucleophile that we reacted with. So, in the case of a substitution reaction, which as you can see, I'm going to label with the number 1, what we are doing is that the nucleophile, which the abbreviation here is NUC, is going to take the place of the halogen, okay? Now, because the halogen is leaving the system, our halogen is going to be a leaving group in a substitution reaction. And like I just mentioned, the nucleophile now is going to be bonded, and I'm going to highlight this in green, to the carbon that was attached to the halogen. When it comes to an elimination reaction, which here I'm labeling with the number 2, what happens is that our nucleophile is going to be a base. And based on the definitions that we have for general chemistry, remember that bases are going to be able to accept protons. And that's exactly what we see. As we go from that base reacting with that haloalkane specifically, what we're going to be reacting with it is going to be a hydrogen that it is considered in the beta position. The reason why we call that position beta is because the carbon atom that is holding the halogen is the alpha position. As you can see, I label both centers. So understand that when it comes to these reactions, the product of an elimination reaction is going to be an alkene. And that's always going to be the case. We're going to have a protonated base, which is the second product that you see. And lastly, we're going to see the anion of our halogen. Because remember, similar to what we saw in the substitution reaction, that halogen is going to be our leaving group. Now, when it comes to the products that we have in a substitution reaction, there's going to be a variety of functional groups that can be produced. There are two main reasons why alkyl halides undergo substitution and elimination reactions. The first one is because the halogen is an electron withdrawing group. Remember, when we look at the electronegativity values between a halogen, which here is in the letter X, and the carbon atom that is bonded to, halogens tend to have a higher electronegativity value. So, what does that mean? That in this case, the bond between carbon and the halogen, that which I highlighted in orange, is going to be a polar covalent bond. In this polar covalent bond, as you can see, we can illustrate the difference in electronegativity by putting those symbols that are like S, which stand for delta. And because our halogen is an electron withdrawing group and it has a larger electronegativity value, we're going to put a delta minus. Our carbon atom, because it's more electropositive, we are going to add a delta plus. Now, having the ability of this electron withdrawing group, making the carbon atom that is attached to partial positive, makes that center, the carbon atom, more susceptible to nucleophilic attack. Now, the other reason why alkyl halides will be undergoing these reactions is because the halogens is going to be acting as a leaving group. So ultimately, it doesn't matter if we do substitution or eliminations, the halogen is going to leave the system. And as I explained in the previous slide, in the case of substitution, we're going to be forming a bond, a covalent bond per se, with the incoming nucleophile, while when we have an elimination reaction, we are going to form an alkene, because remember that we're going to be extracting the beta hydrogen from the system. Let's now go into detail over the different mechanisms that we need to be familiar with for substitution and elimination reactions, starting with SN1 mechanism. So, understand that in the SN1 mechanism, which is nucleophilic substitution 1, we have, for the most part, as you can see, a tertiary substrate, or in other words, a tertiary alkyl halide, as a reactant, okay? Now, here we have, for example, one of the examples of a particular nucleophile that can be present in this type of reaction. And here we have an alcohol. So understand that when we have the SN1 mechanism, this mechanism is going to be occurring in two steps. The first step of the reaction is where the leaving group leaves. This forms a carbocation. And in the case of this example particularly, as you can see, we have a tertiary carbocation. And in this tertiary carbocation, remember that this is the most stable carbocation that we can form. Then, in the second step of the reaction, we're going to have a nucleophilic attack. So, our alcohol is going to attack the carbocation, specifically the oxygen atom in our alcohol, because it is the atom that has lone pairs. That is going to be forming then that covalent bond that I expressed before. As you can see, I highlighted it in green. And in the last step of the reaction, as you can see, we need to deprotonate the particular alcohol that was added in this instance. And as you can see, the substitution product here is going to form an ether. Okay? But remember, when we have substitution reactions, it depends on what is the incoming nucleophile to see what kind of product we're going to form. We can have ethers, we can have alcohols, and we're going to see other examples as we move right along. So, as you can see, we always think about it in, like I just illustrated, that this mechanism happens in two steps, but it's actually three because of the deprotonation at the end. Now, because the nucleophile is also the solvent, that's why this process is called solvolysis. Let's move on to the next substitution mechanism that you guys need to be familiar with, which is the nucleophilic substitution 2. So, in nucleophilic substitution 2, or SN2 mechanism, understand that this mechanism, it is what is called concerted. Concerted basically means that at the same time as the leaving group that the leaving group leaves, or there's a loss in the leaving group, we're going to have a nucleophilic attack. Okay? So, understand that concerted, at the end of the day, what it means is simultaneous. And as you can see illustrated here, we're going to have the nucleophile attack the carbon that is electropositive, and then the halogen, which is our leaving group, is going to leave the system. Now, similar to what we saw in the previous slide, we are going to form a covalent bond between the carbon that was holding the halogen and the nucleophile. The next mechanism that we're going to be talking about, it is an E1 mechanism, which is elimination 1 mechanism. As you can see, in the elimination reaction, we're going to have a tertiary substrate, okay? And similarly, we are going to be having specifically an alcohol as a solvent, okay? Now, in the elimination 1 mechanism or E1 mechanism, similar to what we saw in the SN1, here, the first step of the mechanism is the loss of the leaving group. So the leaving group is going to leave, which is illustrated by the arrow, and we're going to form that carbocation intermediate. Now, since we have this formation of the carbocation, remember, in this case, our nucleophile is going to be acting as a base. And remember, bases, as I just mentioned a few moments ago, are going to be accepting protons. In this case, as you can see, if I label my centers as alpha for the carbon that was holding the halogen and beta to the carbon atom that it is bonded to the alpha carbon, the hydrogen that lives in the beta carbon is the one that gets extracted. And that's how we have an elimination product. And as I mentioned previously, the formation of the product results in an alkene. Now, remember, when we have an E1 mechanism, the ethanol or the nucleophile that we have in this instance is going to be serving as a base, not as a nucleophile. So its role is the deprotonation of that carbocation intermediate in order to form that alkene. The last mechanism that we're going to go over in substitution and elimination reactions is going to be the E2 mechanism or elimination 2 mechanism. Now, when it comes to this, understand that when we have an alkyl halide that is treated with strong base, and you guys should know the different types of strong bases that are out there, which include hydroxide, alkoxides, like ethanol, as you can see, ETO minus, okay? They can undergo beta elimination. In other words, the 1,2 elimination to form an alkene. So remember, eliminations always result in the formation of an alkene. Now, as I mentioned before, the carbon that contains the halogen is alpha. The carbon attached to it is called beta. So these strong bases, when we have an E2 mechanism, what they do is that at the same time that they extract the proton, as we can see in the bottom of the slide, which I boxed in blue, we are going to be extracting the proton, meaning that there's going to be a proton transfer. Then that is going to lead to the formation of the carbon-carbon double bond and the loss of the leaving group. So at the end of the day, this is an example of also a concerted mechanism. It happens all at once. It happens simultaneously. And overall, we form the alkene, we form a protonated base, and the anion for our leaving group.